So what is a hydrate, you ask? A hydrate is a compound. Usually we see it as a salt, but it doesn't have to be a salt. Sometimes there are hydrated gases and things like that. And these compounds absorb water and actually incorporate them into their molecular structure so that the molecule actually has water molecules within it. So they're pretty cool, not gonna lie. And usually these are represented, especially if they're a salt, as AB2 being some sort of salt chemical formula. And then this weird little black dot that I always kind of think of like a multiplication because it's telling you how many water molecules there are per one regular salt molecule. So it's not really a multiplication dot, but it is like I always think of it like a multiplication dot just because it helps me kind of think about what it looks like. And then this X usually represents like a coefficient in front of water. So it might be 2, 5, 6, could be whatever. And they do have names, and we'll kind of see how those are named in the next example. So Epsom salts, which are pretty common, it's like a bath salt, and they're used medicinally to add to a bath to reduce swelling and usually relieve aches and pains. So it's a pretty common hydrate. You might even have some at your house. In labs, hydrates can be heated, which then drives off water molecules because they have a relatively low boiling point. And then by taking the mass of that sample before and after heating, you can basically determine the percent of water that was in that sample. So it's kind of fun. If we were in school, we would do a lab like this. I'm going to try to do a lab like this in my kitchen. So working out the logistics to kind of show you what that looks like. But it's a pretty fun lab. It's really fun with copper hydrates. So if you just type in Google copper hydrate, you'll probably get an image that pops up, and it's really pretty blue. But then when you heat it, it turns white. So it's really fun to use that in lab because you can really tell when the water's been driven off. So yeah, it's really pretty like deep blue. It's nice. So this practice problem actually has a hydrate in it. So it wants to know what's the percent composition of copper 2 chloride pentahydrate. So this last part here, pentahydrate, that's how we know it's a hydrate. The penta comes from those Latin prefixes. Penta means 5, like a pentagon, 5-sided shape. And then copper 2 chloride, hopefully you remember how to do that chemical formula. So take a second, see if you can write the chemical formula for copper 2 chloride. Okay, this is hopefully the formula you got. So copper 2 tells us that the charge on copper is 2. Chlorine always has a -1 charge. If we do our crisscross to balance charges, we should get CuCl2. And then we have this weird little dot. And pentahydrate means 5H2O. So this is the formula of the hydrate that we're analyzing. For percent composition of hydrates, usually we don't break it down into copper, chlorine, hydrogen, and oxygen. We break it down into copper, chlorine, and water. So we're only going to do 3. So we assume that the water molecules stay together. Okay, so for this, since we're not given any numerical data here, we're going to go ahead and use molar masses. Okay, so we're going to find the total mass of the compound. Keep water molecules together just to keep it simple. So since we have 1 copper, we have 1 times the molar mass of copper plus 2 times the molar mass of chlorine plus 5 times the molar mass of water, which is about 18.02. And we should get a molar mass of 224.55 grams per mole. Now that we have our total, we can go ahead and divide this into the 3 parts, copper, chlorine, and water. So for copper, we're going to take the molar mass of copper divided by 224.55 and multiply by 100, and we get 28.3. For chlorine, 2 times 35.45 is about 70.90. We again divide by 224.55, multiply by 100, and we get 31.57%. Now from here, technically, if you wanted to, what you could do is add these two together and then subtract from 100%, and that should give you the percent of water that you would have, okay? But mathematically, if you wanted to do it, what we would do is take 5 times the molar mass of water, divide it by 224.55 grams, and multiply by 100, and we will get 40.12%. So either way, whether you do it through multiplication and division or by adding and then subtracting from 100%, you should get 40.12% of water. This is a different type of question, but another practical practice problem. How much aluminum can we extract from 1.814 times 10 to the 6 grams of aluminum oxide? Okay, so this is a little bit different conceptually. So the first thing I need to do here is to figure out what is the chemical formula of aluminum oxide. Aluminum oxide should be a compound that you can figure out the chemical formula of. So go ahead, take a second and see if you can do that. All right, hopefully you got Al2O3. To find the molar mass, we were doing 2 times the molar mass of aluminum plus 3 times the molar mass of oxygen. Now, since we are only really interested in aluminum, it didn't ask how much oxygen we could potentially extract. I'm going to go ahead and find the percent composition of aluminum in aluminum oxide. Okay, so I'm going to take the molar mass of aluminum, which is the molar mass of the atoms of aluminum that are in the compound, which is going to be 2 times 26.98, and divide by my total molar mass. So that gives me 52.92% of aluminum. Okay, so no matter what sample I have of aluminum oxide, it's always going to be 52.92% aluminum. So in this sample, I have 1.814 times 10 to the 6 grams, that's a lot, of aluminum oxide. If I multiply this by the percent I just found, I will find the grams that is just aluminum. So that's what I'm going to do for my next step. We are taking the part, and that's going to be whole times percent. So our whole again is 1.814 times 10 to the 6. Multiply it by our percent. I just convert it to a decimal there and make it easy. And we get 9.6 times 10 to the 5 grams of aluminum that can be extracted. Okay. For this problem, calcium hydroxide is 43.18% oxygen. How many grams of oxygen are in 165.0 grams of the compound? How many moles of oxygen is this? Okay, so the first part of this question is very similar to the problem that we just did. So you can take a second and work through that. The second part of the question, how many moles of oxygen is this, is a throwback to the stuff on the quiz that we just took, okay? So you should be able to, once you find the grams of oxygen, just convert that to moles, okay? So take a second and do that. Okay, so again, part is going to be equal to whole times the percent. So we have the whole of our sample is 165 grams. And then the percent that we're given, the percent that's oxygen, we just have to multiply that by 43.18%. So that tells us that we have 79.41 grams of oxygen. For the second part, all we have to do is go from grams to moles using dimensional analysis. So we have 79.41 grams. I'm just going to throw that over 1. To go from grams to moles, we're going to be dividing by molar mass. Okay, and what that involves is multiplying by 1 mole and then dividing by 16 grams. Plug that into a calculator and you should get 4.96 moles of oxygen. For this question, we want to know if 235 grams of magnesium can be recovered from 550 grams of magnesium phosphate. Okay, I want you to try to do this one on your own. The first step though we have to do is find the formula of magnesium phosphate. If you don't remember what phosphate is, I will go ahead and throw that formula up on here. Okay, so we have magnesium 3 times PO4 with a 2 outside there. So that's their chemical formula you'll be using. And we want to know if we can get 235 grams of magnesium from a 550 gram sample. Here I've given you the total molar mass. So to do this, if you're having trouble thinking about it, the first step I would do is find what percent of magnesium makes up magnesium phosphate. Okay, so that's the first step. Then remember the part that you're interested in, the amount of magnesium, is going to be equal to the whole, which is 550, times the percent that you found of magnesium. And then from there, we know how much in grams of magnesium can be extracted from a 550 gram sample. Okay, so then you're just going to compare that number that you get to 235. Is it greater than, equal to, or less than? And that should help you answer the question. So take a second and work through this problem. And then once you're done, you can check. Okay, for your percent magnesium, remember we have 3 magnesium, so we have 3 times 24.31 in our numerator here, divided by the total grams of the molar mass of the compound magnesium phosphate. And that tells us that we have 27.74% of magnesium phosphate is actually magnesium. Then I'm going to take that 27.74 and multiply it by my 550 grams. That tells me that I've gotten 152.57 grams of magnesium that can be extracted. Because 152.57 is less than the 235, which is what they're asking, I can say that no, we cannot extract that much magnesium because we can only get 152.57 grams of magnesium. Okay, so that is our introduction to percent composition. We'll be doing some more problems and things like this. And again, later on using this to figure out how we can actually calculate what the chemical formula is for a substance based on numerical data like this. Okay, have a great day, guys.